video, we're going to be talking about differential equations. So let's just go ahead and define what a differential equation is first. So a diff eq is an equation involving an unknown function, y equals f of x, and one or more of its derivatives. Now, a solution to a differential equation is a function that satisfies the differential equation when f and its derivatives are substituted into the equation. All right? So I guess like a general idea of what's happening here, all right, is let's consider y prime equals 3x to the second. Now, this right here is a differential equation because it includes its derivative and a function of x or something like that. All right. Now, there is a relationship between the variables x and y. So let me write that down. There is a relationship between x and y. Oops, sorry. And y is an unknown function of x. Meaning y is going to equal some function of x. That's what that means. Now, if we look on the left-hand side of the equation, notice here we have its derivative, or we have a derivative, and we know this derivative is equal to 3x to the second. So what function has a derivative that is equal to 3x to the second? That's really what we're asking. So what function, I'm going to write this in red. What function has a derivative of 3x to the second? And if you just take a second and you think about it, I think you will come to realize that that magical function is just y equals x to the third power. So this is considered to be a solution to our differential equation y prime equals 3x to the second. Now, how do we verify this? Well, remember, if we go back to this definition, all right, all the way up top here, remember, a differential equation is an equation involving an unknown function of x and one or more of its derivatives, and a solution to the differential equation is a function y equals f of x. It's an unknown function that satisfies the diff eq when f and its derivatives are substituted into the equation. Watch what happens here. We have the differential equation y equals 3x to the second. Or I'm sorry, y prime equals 3x to the second. We know what y is. Okay? Like we know what y is. So how do we actually get this? Well, if you just integrate both sides of this differential equation, on the left-hand side, you're going to get the original function back, or you're going to get the original equation y. And on the right-hand side, if you integrate this with respect to x, you get that 1/3 x to the third. All right, but remember, we have a 3 out front, so the 3's reduce. And that's how we got this. So it's actually very simple when you really take a step back and you think about it. All right. But there's a little bit more going on in this. Like, hopefully you're sitting there saying, well, what happened to the plus c? All right. And we will worry about this in a little bit. All right. We'll worry about that later. For now, I just want us to be able to recognize when we have a differential equation and then when we don't have a differential equation. Okay. So we're going to move into what's the next part of learning diff EQs is just verifying solutions. In fact, you did this a long time ago. I don't know if you remember when you were in algebra class. and they said a question like this. Is x equals 1 a solution to x minus 2 equals 3? All right? And what you would do is you would take x equals 1, you would substitute it in, and you would say, well, 1 minus 2 is negative 1, which does not equal 3, so you would say, no, x is not a solution. We're going to do the same exact thing here, it's just we're using differential equations now. So just give me a second, I'm going to erase this. And the problem that we're going to look at is right here. So we're going to verify that the function y equals e to the negative 3x plus 2x plus 3 is a solution to the diffq, or differential equations. I'm just going to write diffq y prime plus 3y equals 6x plus 11. Now, to verify this, remember, you're going to take this function of y, which we have right here, and its derivative, and substitute it into the equation. In other words, we need to find y prime. We already have y, which is e to the negative 3x plus 2x plus 3. And the only thing that we're going to do here is once we know what they are, or once we find our derivative, we're going to substitute it in, and we're going to see, does the left-hand side equal the right-hand side, or can we get a very nice simplification here? Okay? So, if y equals e to the negative 3x plus 2x plus 3, y prime has to equal e to the negative 3x times negative 3 plus 2, which I'm going to rewrite this as y prime equals negative 3 e to the negative 3x plus 2. So now that I know what the derivative is, and I know what y already is, I'm going to go ahead and substitute them into my diffeq. So let's write out the diffeq again one more time. We have y prime plus 3y equals 6x plus 11. Y prime, we know, is negative 3 e to the negative 3x plus 2 plus 3 times y. Y is e to the negative 3x plus 2x plus 3. And what we are hoping is when everything is all said and done, this will equal 6x plus 11. So let's go ahead. We can remove the parentheses by distributing. So we get negative 3e to the negative 3x plus 2 plus 3e to the negative 3x plus 6x plus 9. And that should equal 6x plus 11. And when you look at this here, we have negative 3e to the 3x, positive 3e to the 3x. We know they reduce to 0. We have 6x out front, and 2 plus 9 is 11. And notice we get what we call in mathematics a tautology, or the left side equals the right side. So we verified the solution. And that's it. That is, I don't want to say that's as easy as it gets, but that's what this is, okay? Now, you got to understand one thing, though, here, all right? I gave you the solution. I said verify that this function is a solution. Up above, with this very simple problem here, I didn't give you this. We actually kind of guessed what it was because we asked the question, what function has a derivative of 3x to the second? And that was really easy for us to kind of wrap our head around in terms of, oh, well, that's going to be y equals x to the third. But if you remember, if you take the derivative of y equals x to the third, you get y prime equals 3x squared. And if you were to take the original diff EQ, which is right here, and just substitute it into the derivative, you would get 3x squared equals 3x squared, which is exactly what you would expect. Okay? Now, the next thing I'm going to go over here is how to find the order, which is a way that we classify differential equations. So we classify, and there are other ways too, but since we're just learning this, we're going to keep it simple. So we classify differential equations by their order. And yes, like I said, there are other ways too. Like we have order, we have degree, we have partial, we have linear, we have nonlinear. So there's all these different types of ways that we can classify diff EQs, but we're going to start by the easiest one, which is by their order. So the order of a differential equation is the highest order of any, any derivative of the unknown function that appears in the equation. All right. So I'm going to do like 3 little simple examples here. Directions are really simple. What is the order? So for the first one, part A, we have y prime minus 4y equals x to the second minus 3x plus 4. Now, I'm going to tell you right now, the order is 1. But let's understand why. So, come back to the definition. The key to studying math, and this goes from the very start of math until you are done, is understanding the definition. That's it. Being able to apply the definition to any problem you've ever seen. That's what math is all about. So, the order of a differential equation is the highest order. So, it's the highest order of any derivative. So, if we look at our problem right here, here's a derivative, and that is y prime. It's first order. So, that would be like another way we would say this. First order. Okay? And yes, there are first order, second order, third order. The most famous one you probably already know and you didn't even realize it, which I'll show you at the end of this one. Because I got 2 more examples here. So we got x to the second, y triple prime minus 3x y double prime plus xy prime minus 3y equals sine x. Now, in this scenario, the order is 3. And the reason is right here. That is a third order derivative. So, the order is a 3. Now, the last example here, we have 4 over x. And anytime you have an exponent that is in parentheses like this, that's a derivative. All right? Like, that is the notation we use from here on out. Okay? So, this y is the 4th derivative. Minus 6 over x squared, y double prime, plus 12 over 4, or 12 over x to the 4th y equals x to the third minus 3x squared plus 4x minus 12. And this order is fourth order. And the reason is this right here. And remember, from here on out, when you have an exponent, or at least it looks like an exponent, but it has those parentheses around it, okay, that is considered to be a derivative. All right? Now, earlier I mentioned, one of the most famous second order differential equations. Well, you know it as F equals ma, which is Newton's second law of motion, right? And if you've taken a physics class, calculus based, of course, they would probably write this as F equals m times the second derivative, which is d2y over dt squared. So this is a second order derivative. All right. And like I said, we have other ways, like we have linear and nonlinear. You will learn the differences between linear versus nonlinear. I don't know why I put a period there. You will learn the differences between linear and nonlinear in the actual class called differential equations. All right. For now, we are just going to focus strictly on first order and how to solve them and stuff like that. All right. So earlier I said, let me just show you. Earlier I said, this plus C thing, we're going to worry about this later. Here's where it actually comes into play. All right. And if you remember from Calc 1, even at the very beginning of this semester, okay, when I was talking about indefinite integrals and how, there's more than one solution, that's because you get what we call a family of integral solutions. So let me show you what this means, all right? Basically, we have two types of solutions. We have the first type, which is a general solution. All right. And this is where you have the function of x plus some constant. All right. Or you get y equals this function of x plus some constant. Then you have the second type. The second type is what we call a particular solution. Now, a particular solution, all right, is where you have basically a specific solution or a specific part of the graph that you want. Like, for example, we learned that the solution to that very first differential equation was y equals x to the third, right? But if I say it's x to the third plus 1, this is a particular solution. It's because we know exactly what that plus c is. In this case, it's 1. All right, and I'm going to show you how to find all this stuff in a little bit. But the idea behind this, okay, the idea behind this is, excuse me, that when you have this plus c thing, you got a general solution. If you know exactly what you're talking about, though, all right, you have particular solutions, all right? And let's see, I guess I can show you this in Desmos. It's really not that difficult. So if we went into Desmos, and like I said, we just graphed y equals x to the third. And we know that's exactly what it looks like, okay? Well, the problem is you got that plus c thing. And when you put the plus c, you can actually, in Desmos, you can add a slider. And you could see, when c equals 1, this is the equation that you get. When c equals 5, this is the graph that you get. And you have everything in between that as well. So you could just let this slide up and down depending upon what C is. Each different value of C is considered to be a different member of the family of solutions. So this is what we're actually going to be looking at, all right? So let's go ahead and let's do a very simple example. We're going to want to find the particular solution. So this is a specific one. Let's find a particular solution to y prime equals 2x passing through the point 2, 7. Now, before we even get started with this, I really want you to understand what's happening. Here, we have a differential equation. That y prime is a derivative. The point 2, x refers to x and y. But if you look at your differential equation, you do not have y yet. You have y's derivative. We have y's derivative. So before we can even use the point 2, 7, we have to find the unknown function of y, whose derivative is 2x. So let me write that out. All right, because this, like I said, once you understand this basic concept, then DiffEqs become very simple. So what we have is the following. We want to find the unknown function y equals f of x, whose derivative is equal to 2x. And like I said, if you just think about this for a second, because this is a very simple one, we know that that unknown function of y has to be x squared plus c. And this right here is the general solution. And it's general because of the plus c. This will generate all integral solutions. And those solutions belong to the family of solutions. Okay? But we want to know what is C, because we were asked to find the particular solution. So to find the particular solution, use 2, 7 and substitute into y equals x squared plus c. So wherever we see y, we're going to put a 7. Wherever we see an x, we're going to put a 2. Remember, always put your parentheses first whenever you're making a substitution with exponents. So you end up getting 7 equals 4 plus c, or c equals 3. Therefore, and I'm going to use this, I'm going to use these nice 3 little dots. That stands for the word therefore. Might as well start teaching you some math notation. Therefore, our particular solution to y prime equals 2x is y equals x squared plus 3. And this is the parabola that will pass through the point 2, 7. All right. In the next section, we're going to look at direction fields, and you're going to see like how unbelievably awesome these things look when you graph them. It's like super, super cool. Now, the last thing I want us to go over are just two more problems, which would be an initial value problems. Or IVPs for short. So usually a given differential equation has an infinite number of solutions. Remember, when we did this y equals x squared plus c for the previous problem, there are infinite solutions to this. C can be anything we want it to be. C can be anything we want it to be. So it's very normal to ask, well, which one do we want? You know what I mean? Like, okay, well, if there's an infinite number of solutions, which one do we want? So to choose this solution, we need some information. We just need a little bit of information, all right? So the specific information that we can use or that we can be given can be useful, and we can consider that to be an initial value, all right? So let's just recap what we're saying here. First, you found the solution to some differential equation. We're going to call it, I'll write it in red, y prime equals 2x. That's the diff EQ we had. We found the general solution to be y equals x to the second plus c. On the surface, this has an infinite amount of solutions because c can be any number between positive and negative infinity. So the question becomes, all right, well, in order for this to be useful, we need an actual specific value. So which one do we want? We need some info. We need some starting values. And to simplify that, we just call them initial values, hence the name initial value problems. Okay? So the first thing that we're going to do here is we're going to verify that we have basically an initial value problem. So verify that y equals 2e to the negative 2t plus e to the t is a solution to the initial value problem y prime plus 2y equals 3e to the t, where our initial values is y of 0 equals 3. So go ahead, write that down. I'm going to repeat it one more time. Verify that y equals 2e to the negative 2t plus e to the t is a solution to the initial value problem y prime plus 2y equals 3e to the t with initial values y of 0 equals 3. So once again, in this example, I am giving you an answer. I am saying, listen, this is a solution. I want you to verify it. Demonstrate to me that it is a solution and include the initial values here. So if you look at the differential equation, y prime plus 2y equals 3e to the t, notice we already have y. We know what this is. We know what y is. What we don't know, what is y prime? Therefore, the first thing we're going to have to do is we're going to have to take y equals 2e to the negative 2t plus e to the t, and we're going to have to find its derivative. So the derivative is going to be y prime equals, oh, that's a horrible looking y prime. Y prime equals negative 4 e to the negative 2t plus e to the t. All right, remember, chain rule multiplied by negative 2. Next, we are going to substitute both y prime and y into the differential equation to verify that we get 3e to the t on the left and 3e to the t on the right. So let's go ahead, let's do that. So y prime plus 2y is going to equal, let me put my parentheses first, make my substitution. Y prime is going to be negative 4e to the negative 2t plus e to the t plus 2 times the quantity of y, which was 2e to the negative 2t plus e to the t. Now we're going to go ahead and distribute. Negative 4e to the negative 2t plus e to the t plus 4e to the negative 2t plus 2e to the t. Please note you have negative 4e to the negative 2t plus 4e to the negative 2t. They are going to reduce. And when you group all your like terms, you get 3e to the t, which is exactly what you wanted. All right. So now that we know that this is a solution, we can go ahead and figure out, we could verify that this actually works for the initial value problem, because we need to calculate y of 0. All right. So we know that this is a solution. We just verified it. Now let's verify it for the initial values as well. So y equals (2e to the negative 2t). Sorry, I lost my place there in my notes. And we want to verify it for this. In other words, we want to make sure that when we substitute in t equals 0, we get 3 on the left-hand side. Well, if you recall, e to the 0 is 1. So you get 2 plus 1, which is definitely 3. So the results verify the initial value as well. And this is how we verify initial value problems. First thing we do, we take the solution they gave us and we verify to make sure it works in the differential equation. Then we take that solution and verify that the initial value works as well. Okay? Like I said, it's very cool once you start thinking about this, or once you start looking at it like this. And what's really interesting, all right, is when you go ahead and you start graphing these things. So let's think about this. In this example, the first part, so in the previous example, we had y prime plus 2y equals 3e to the t, where our initial value was y of 0 equals 3. Now, when you take, and this is what I mean by you get the integral solutions, or the family of curves, all right? The general solution to this problem right here, the general solution, and I'm just going to give it to you. We're going to learn how to figure it out later. But the general solution is 2e to the negative 2t plus ce to the t. This is our general solution. All right? And watch how this changes for us. So we're going to go back into Desmos real fast. We're going to get rid of these two things. And I'm going to type in the general solution. Y equals 2 e to the negative 2t plus c e to the t. And we're going to add a slider for c. Now, initially, let me see if I can. There we go. That looks better. Now, initially, when c equals 1, this is what that solution looks like when you graph it. But watch what happens when I change what c is. Oops. There we go. So notice here, it looks like it's a parabola that gets like narrow, but as c gets smaller, it actually flips down and goes down to negative infinity. It's really interesting how these things work. And like I said, it all depends on what exactly is your initial condition. All right. I don't want to jump too far forward, but I'm going to go ahead and do this anyways because I want you to see what this looks like. All right. When I go ahead and I graph a direction field, can I use this one? Oh, I don't like this one at all. I was using that one earlier. Yeah, that's the one I want. All right. So when I go ahead and graph our differential equation that we had previously, now we're going to go back to our notes real fast because I want you to see the differential equation. It's y prime plus 2y equals 3e to the t. Okay? Watch what this actually looks like when I graph it. So you're going to have to give me 1 second here. All right. So it's going to be y prime equals 3e to the t. I got to do a little bit of maneuvering here. Minus 2y. And our initial condition is 0, 3. And let's zoom in here so you can actually see this. All right, there we go. I think this looks okay. So this is kind of foreshadowing into the next section, but here's what I want to demonstrate. All right. All of these little tick marks that you see within the body of this graph, all right, they all represent what we call isoclines or derivatives. So like, for example, the derivative at this point right here is negative. And you can see that because it has a negative slope at that little specific point. But if you just move one x value to the right, the derivative at this point right here turns positive. All right? This is what differential equations look like when you graph them. At every single point, you got to remember, a derivative is the slope, it's the rate of change. So at each different xy value within this field, all right, there's different derivatives. And I can kind of intensify this a little bit and make them a little bit longer so you can kind of see them. And if I were to take our initial value of a comma 3, I'm sorry, did I say a comma 3? 0 comma 3, and I were to change it, you will see how this integral curve right here, this is our first solution. If I move it down here, notice how it changes just by changing the initial conditions. So anytime you change the initial condition, you end up getting a completely different integral solution, or you end up getting a completely different function of y, which is fascinating. All right. And these things, they all look like really interesting and really cool when you start messing around with them a little bit. I think, which one do I like? I think it's sine of x plus y. I think I like that one. Yeah, this one's kind of neat. All right. And you can see here that when I change my initial value, you can see how that curve changes. And the closer and closer you get down here, the closer it becomes a straight line. All right. If you go on the other side, it's the same thing. So you can see like here and here, these are they're slanted asymptotes. So this could be like how, I don't know, fluid moves through a pipe. All right, that's exactly what that would look like the turbulence or something like that. You can even switch it up. Let's make it instead of x, we'll do x to the second. See how that changes things. Oh, look at that. There you go. So now the whole thing changes. I mean, it's just absolutely fascinating when you really start to mess with these things. But I don't want to go too far down the rabbit hole. That's next section. Let's go back to our notes here. Here we go. So how do we solve an initial value problem? Well, it's not that difficult. We're going to do this from left to right. So we have y prime, which equals 3 e to the x plus x squared minus 4, given the initial conditions, y of 0 equals 5. All right, which when you have this notation right here, everyone, all this is saying is when you have the point 0, 5. That's it. So the first step in solving an initial value problem is to find the general family of solutions. So the first thing we're going to do is find the general solution. Now to do this, we take our differential equation, all right, excuse me, and we are going to integrate both sides. So we're going to find the antiderivative of both sides of the differential equation. So we're going to integrate the left, and we're going to integrate the right. All right. Now we integrate both of these with respect to x. And when you do that, on the left-hand side, you're going to get y plus a constant. So I'm going to put c1. Because on the right-hand side, when you integrate this, you get 3e to the x plus 1/3 x to the third minus 4x plus another constant. All right. Now, we're able to integrate both sides because the term y appears by itself, which is key. So we could do this right here. Because the y term is on the left-hand side. That's easy. Now, we're going to solve this for y by subtracting c1 from both sides. Now, for us, we're going to say where k equals, actually, you know what? Let's leave it simple. Where c equals c2 minus c1. All right. So what we're going to do is we're just going to replace c2 minus c1 right here with just a general constant c, because if you think about it, a constant minus a constant is another constant. All right. So we get y equals 3e to the x plus 1/3 x to the third minus 4x plus our constant. So this is our general solution right here. All right. So like I said, it's very straightforward. You're just integrating the left, you're integrating the right, you're combining the constants to make like a general constant, and we just found our general solution by solving for y. The second thing is to find a particular solution. So to find a particular solution, use y of 0 equals 5. So we get 5 equals 3 e to the 0 plus 1/3 times x to the, or I'm sorry, 1/3 times 0 to the 3rd minus 4 times 0 plus c, which gives you 5 equals 3 plus c, and when you subtract 3 from both sides, you get c equals 2. Therefore, our particular solution is y equals 3e to the x plus 1/3 x squared minus 4x plus 2. And that is going to be it for this video. I'll follow up this video with the next section, which deals with direction fields and things like that. The next section isn't too bad. It's just we're going to have to learn how to graph these things. And it's, like I said, it's very simple once I show you. So, see you in the next one.